Electrophiles and nucleophiles react, one accepting and the other donating electrons in order to form a covalent bond. When both electrons are donated to form a bond between a nucleophile and electrophile, it is known as a coordinate covalent bond. An easy way to represent the movement of electrons from nucleophile to electrophile is a curved arrow notation, where the arrow starts at the nucleophilic center, ending at the electrophilic center. There are three possible ways an electron can flow. It can originate from a lone pair and then be used to form a bond. It can originate from a bond and be used to form a lone pair, or it can be used to form a bond originating from a bond. Nucleophiles and electrophiles can also be located on the same molecule. When this happens, they can react quicker than when they are located on different molecules. That's just because of the close proximity. Other times, a certain type of molecule, like water, can act both as a nucleophile and an electrophile in different instances, also known as an amphoteric molecule. A molecule's strength is affected by multiple factors like the solution it is in, as well as how electron-rich or poor it is, and how easily it can accept or give up those electrons. So electrophiles are electron-loving atoms, meaning that in a reaction, these are the atoms of a molecule that accept the electron or a pair of electrons in order to form a covalent bond. The electrophile uses its low-energy unoccupied molecular orbital when bonding with a base. Because electrophiles want to gain an electron, they will have a positive charge, or a cation. Other electrophiles can be atoms, ions, or molecules with an incomplete octet of electrons. This means that they want to gain an electron to fulfill the octet. Or they're molecules with central atoms that do not follow the octet rule, so they can have more than 8 electrons. Or molecules that have multiple bonds between two atoms of differing electronegatives. This means that the electrons are being drawn away from that central atom. Another term for electrophile is a Lewis acid. An electron pair acceptor and a subcategory of electrophiles are Bronsted acids. The reactants in a reaction that donate the proton and therefore accept an electron or a pair of electrons. The electrophilicity is how well a species can accept a lone pair of electrons, which is determined by its electron richness or electron poorness of an atom. Another term for electrophilicity, or like a similar term, is acidity. Right here, this is going to be a reaction with a cation or with an electrophile. These are all different examples of electrophiles. You can see here this carbon has a positive charge, meaning that it wants to gain electrons really badly, and to get a neutral charge, right? And you can see also here that it's bonded to an oxygen, meaning that it wants to gain more electrons because its electrons are being pulled towards the oxygen. So that's why it has a positive partial charge. So going on to nucleophiles, or nucleus-loving molecules, they are reactants that donate the electrons to react or form a covalent bond. The nucleophile's highest energy occupied molecular orbital interacts with the acid's lowest energy unoccupied orbital to create bonded molecular orbitals. Another term for a nucleophile is a Lewis base, or an electron pair donor. A more specific category of nucleophiles are Bronsted bases, which are the reactants in a reaction that donate a pair of electrons to a proton, H+. Because nucleophiles donate the electron, they are rich in electrons, or they are negatively charged, which we can see here. All of these are all examples of nucleophiles, are all negatively charged, or have partial negative charges, as shown here. The stronger the nucleophile, the more unstable or reactive it must be. Therefore, things like resonance and steric hindrance affect a nucleophile's strength. Nucleophilicity is how well a species can donate a pair of electrons determined by the electron's richness or poorness. So again, this is similar to basicity. The more electronegative the element is, the more tightly it holds onto its electrons, and therefore the lower the nucleophilicity. But if you go down the periodic table, the nucleophilicity changes based on the solution. You would think that the nucleophilicity would decrease because when you go down, the radius increases a lot. So that means that the negative charge is spread over a lot larger area, decreasing the nucleophilicity because the electron or the atom will be a lot more stable. However, this is not the case since it depends on the type of solution it's in. When it's in a product solution or a product solvent, then the smaller the atom's radius, the weaker the nucleophile. While if it's in a molecule, in a polar product solvent solution, the opposite is true. Alright, so now to the comparison model. Nucleophiles and electrophiles are comparable to the southern and northern ends of magnets, or the positively and negatively charged portion. Just like how these two ends of a magnet are attracted to one another, the nucleophile and electrophiles are attracted to one another. Additionally, the positive charged portion connects to the negatively charged portion, similar to how the electrophile and nucleophiles react in acid-base reactions. Magnets have one positively charged and one negatively charged end, similar to amphoteric molecules, which have a nucleophilic and electrophilic end. Lastly, a magnet's strength can be altered similar to how a nucleophile and electrophile strength can be altered, depending on the molecule stability or how easily an atom gives up an X or accepts an electron. A stronger nucleophile or electrophile will be able to react more easily and more vigorously because it can more easily react than a weaker nucleophile or electrophile. This is similar to magnets since a stronger magnet will be able to attract to its opposite with a greater distance between them than a weaker magnet. So applications of electrophiles and nucleophiles, electrophiles and nucleophiles make up a lot of molecules that undergo acid-base reactions. Since this is a very broad definition for acid-base reactions, a lot of reactions fall under this category. This encompasses basically any reaction where one molecule donates an electron or electron pair, the base, and another accepts an electron or electron pair, the acid. In this type of reaction, the nucleophile donates the electron, and the electron pair is there for the negatively charged and electron-rich molecule. The electrophile, on the other hand, accepts the electron or electron pair, so it is therefore usually a positively charged or an electron-poor molecule. So in this example right here, we see the nucleophile, it's negatively charged, and it binds to this molecule over here, the electrophile, which gains the electron, and then it goes through a second reaction where the electron in the bond goes to the bromine, so in the end it formed a bond and it broke off a bond to form the new molecules. Thank you.